All right, it is History of Mathematics time, lecture 17. And as I noted on the page, our second midterm exam will be in 2.5 weeks on Wednesday, April 17th. And I was asked to do on homework 6, problem 1, which is to use Newton's binomial theorem to compute the first 5 terms of some expressions. So let's just recall, first of all, the binomial coefficient. Let's say x choose k, which is x minus 1. You start with x and you take the product of a total of k terms, each decreasing by 1. So x minus 1, x minus 2, down to x minus k minus 1, which is x minus k plus 1 over k factorial. And the old binomial theorem says how to expand 1 plus x to the power n. This is 1 plus the binomial coefficient n choose. So is there a question?
No, sorry.
Second. So 1 plus the binomial coefficient n choose 1 times x, n choose 2x squared, n choose 3x cubed, until you get to the last term, which is going to be, if n is a positive integer, n choose n, which is 1 x to the n. So this is the old binomial theorem, which you should know and love. And Newton's binomial theorem says exactly the same thing, but let me just change the exponent to, maybe x was a bad choice of the letter here. Maybe I should have called this a choose k, a minus 1, a minus 2, a minus k plus 1. If you take 1 plus x to the power a, this is still going to be 1 plus a choose 1x, a choose 2x squared, a choose n, x to the n for any n, but it keeps on going. A choose n plus 1, x to the n plus 1, x to the n plus 1. Sorry, a choose x n plus 1, x to the n plus 1. It goes on forever because, I mean, if a is a positive integer, once you get to terms with the power of x bigger than n, all these coefficients are 0. But if a is not a positive integer, you have an infinite series. This is for all a, any real number a, real number, right? And what you get in general is an infinite series. So that's the great theorem, or not the great theorem, that's Newton's binomial theorem from the previous chapter. So suppose we want to expand 1 over 1 plus x squared. Sorry, 1 over 1 minus x squared. So this is 1 minus x squared to the power minus 1. Or if you like, if I want to use a plus sign here, this is 1 plus minus x squared to the minus 1. So it's exactly of this form where a is equal to minus 1, that's the exponent, and instead of x, we have minus x squared. So this is going to be 1 plus minus 1 choose 1 minus x squared plus minus 1 choose 2 minus x squared squared plus minus 1 choose 3 minus x squared cubed plus minus 1 choose 4 minus x squared to the fourth. Those are the first 5 terms, okay? So before I calculate this, you have to make sure you understand how I got this. This is the binomial theorem, and I'm using the exponent a, and my x in this case, in this example, is minus x squared. Right? So let me do this in 2 steps. This is 1. This is minus x squared. So it's minus 1 choose 1 x squared plus minus 1 choose 2 minus x squared squared is x to the fourth. This is minus x squared cubed is minus x to the eighth, and the coefficient is minus 1 choose 3. Minus x squared to the fourth is x to the 16th. So these are the first 5 terms, but I have to know what are these coefficients. So minus 1 choose 1 is minus 1 over 1 factorial is minus 1. This is the binomial coefficient. When k is 1, it's just a over 1. In this case, the a is minus 1. Minus 1 choose 2. You take 2 numbers in the numerator, starting with minus 1 and going down by 1. So if the first term is minus 1, the next term is minus 2 over 2 factorial, which is 2 over 2 factorial, which is 2 over 2, which is 1. Minus 1 choose 3. The denominator is 3 factorial. Minus 1 minus 2 minus 3. This is minus 6 over 6, or minus 1. Minus 1 choose 4 is minus 1 minus 2 minus 3 minus 4 over 4 factorial. This is just 4 factorial over 4 factorial, which is 1. So this coefficient is minus 1. I get 1 plus x squared. Minus 1 choose 2 is 1 plus x to the fourth. Minus 1 choose 3 is minus 1. Minus times minus 1 is plus x to the eighth. Minus 1 choose 4 is plus 1 plus x to the 16th. So one over 1 minus x squared, the first 5 terms are these. So you have to do the algebra correctly, but you get this nice result. Any questions about that? Do I need to do any of the others?
No, thank you.
Okay. So on Wednesday last week, I started to talk about the chapter on the Bernoullis. So this is chapter 8, which is the Bernoullis. There are 2 brothers. At the harmonic series. So if you start to add up the unit fractions, 1 plus a half is 3 halves. Add a third, add a fourth, add a fifth. At any finite point, you can add them up. And the question is, what happens if you go on forever? So this infinite series is the harmonic series. And these are sort of mysterious when you have a sum of infinitely many terms. Each individual term, what is the nth term? The nth term is 1 over n. So each term is getting smaller and smaller and going to 0, but it's not clear what happens to when you keep adding this. Every time you add a number, you get something a little bit bigger. And the question is, do those sums have an upper bound? Do the sums, as we say now, converge, or do they go to infinity? So there is the basic example, which you absolutely have to already know because it came up in calculus, which is the geometric series. So a geometric series is a series where you start with 1 and you add a number. Let's see what there's any notation that's used in the text or whether I need to pick my own. Well, x is always a good number. 1 plus x squared plus x cubed plus x to the 4th and so forth. This is what is called a geometric series, all right? And the question is, does this series converge? Or does it diverge? Or maybe, depending on the x, it converges or diverges. So you can ask, for what x does this series, it's an infinite series, converge? And there's a nice way to solve this problem, which is the following. Let's see.
What makes this specific example a geometric series?
That's the name of it. That's what it's called. Like it could be called John or it could be called Mary, but it's called geometric. I mean, there are geometrical things you can associate with this if you like, but it's called the geometric series. And let me just use the notation in the text. So in the text, they don't start with 1, they start with the first element. And instead of x, they use alpha. So for what alpha does the series converge? You have alpha squared, alpha cubed, alpha to the 4th. And you just keep going, alpha to the n plus 1, out to infinity, right? And that's the series. And the question is, for what alpha does this converge? Now, for example, suppose you let alpha equal 1. Then every power of alpha is 1. So this series is 1 plus 1 plus 1 plus 1 plus 1. You keep adding 1. So the partial sums are 1, 2, 3, 4. This certainly goes to infinity as the number of terms goes to infinity, right? So this series diverges for alpha equal 1. Right? You could ask, what happens for alpha equal minus 1? You get minus 1 plus minus 1 squared plus minus 1 cubed plus minus 1 to the 4th plus minus 1 to the 5th and so forth. That's minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. Does that series converge or diverge? So if you start adding up the terms, you get minus 1. You get minus 1. The next term, if you add the first 2 terms, you get 0. The first 3 terms, you get minus 1. The first 4 terms, they add up to 0. The first 5 terms add up to -1. The first 6 terms add up to 0. So the partial sums oscillate from -1 to 0 to -1 to 0 and so on forever. So even though this partial sums are bounded, the sequence of partial sums doesn't get closer and closer to any number. So this series diverges also. So this series diverges for alpha equal -1. Right? So you can diverge because you go to infinity, or you can diverge because when you start adding the terms, they oscillate between different numbers, but they don't approach any limit. So again, this is all supposed to be review from Math 176, where you talk about infinite series, but I'm not really assuming that you remember anything, but it should be familiar to you. So if you have a series, alpha 1 plus alpha 2 plus alpha 3 plus alpha n and so forth, suppose we let Sn be the sum. So this is what is called the nth partial sum, which is the sum of the first n terms of the series. And we say the infinite series, which you usually write as summation alpha n goes from 1 to infinity, converges if the sequence of partial sums, that is the limit of these partial sums as n goes to infinity, exists. Right? So this is what they taught you in Calc 2. An infinite series converges if the partial sums have a limit. Now, suppose we go back to the geometric series. So let's assume, or let's just let S be the sum of the terms of this sequence. And for simplicity, we can suppose that alpha is positive. No, it doesn't matter. Right? So let S be the sum of the series. If you multiply S by alpha, you're multiplying every term of this series by alpha. You get alpha squared plus alpha cubed plus alpha to the 4th plus alpha to the 5th and so forth. Right? So take this number and multiply it by alpha. And if you subtract S minus alpha S, when you take this series and subtract this series, all these terms cancel these terms, and you're just left with alpha. So S minus alpha S is equal to alpha. Of course, S minus alpha S, if you factor out the S, you get 1 minus alpha S. So if this series converges, then the sum of the series S is alpha over 1 minus alpha. So let's take the famous example, which goes back to the Greeks. Suppose alpha is a half. Then alpha plus alpha squared plus alpha cubed and so forth is a half plus a 4th plus an 8th plus a 16th. You're just summing over the reciprocals of the powers of 2. When alpha is a half, the limit S is a half over 1 minus a half, which is a half over a half, is 1. Right? But that's just what you learned in maybe even pre-calculus, because when you take these, when you add up these sums, you get a half, 3/4, 7/8, 15/16, 31 over 32. These are certainly approaching 1. So, for example, when alpha is a half, this is what you get. Any questions about this? That is, I assume everyone knows that when you start adding up these fractions where the denominators are the powers of 2, the sum is approaching 1. Okay? That's when you take alpha equal 1/2. What about when you take alpha equal 2? So then you would get 2, then you're taking the powers of 2, 2 plus 4 plus 8 plus 16 plus 32 and so forth. And according to this formula, this should add up to 2 over 1 minus 2, which is 2 over minus 1, which is minus 2. And now you should say something has to be wrong, because if I start adding up the powers of 2, that's certainly going to infinity. It doesn't add up to minus 2. So what is wrong here? So that's really an interesting question. And you learn the answer to this in Calc 2, I hope, which is if the series converges, this is the limit. But here we're assuming the series converges and we find the limit. The series doesn't necessarily have a limit. So how can you figure out when the geometric series has a limit? So all we have to do is modify this argument a little bit. So this is from the 19th century, or maybe even the 18th century. And people had to be very careful about what they did, because what seems like a good argument doesn't always give results that hold all the time. So if this geometric series converges to S, when you're taking the sum of the powers of alpha, the limit of the series, the sum of the infinite series, is alpha over 1 minus alpha, which is perfectly fine for 1/2, but obviously fails when alpha is equal to 2. So let's modify this slightly. Suppose we let Sn be the sum of just the first n terms of the series. So you can always add up a finite number of terms. There's no problem about that. And if I take this and multiply it by alpha Sn, when I multiply, I get alpha squared plus alpha cubed plus alpha to the 4th up to alpha to the n, and the last term will be alpha to the n plus 1. And now I subtract Sn minus alpha Sn. When I subtract, these n minus 1 terms cancel these n minus 1 terms. And what I'm left with is alpha minus alpha to the n plus 1. And if I factor out the Sn from this is 1 minus alpha Sn. So if I divide by, so for alpha different from minus 1, if alpha is 1, you're just adding 1 plus 1 plus 1. So we know that diverges. If alpha is not equal to 1, then I can divide by 1 minus alpha. I get Sn is alpha minus alpha to the n plus 1 over 1 minus alpha, which is alpha over 1 minus alpha to the n plus 1 over 1 minus alpha. That's what Sn is. And the question is, what is the limit of this as n goes to infinity? So I'm letting n going to infinity, n goes to infinity, alpha over 1 minus alpha to the n plus 1 over 1 minus alpha. This is a constant. That doesn't change. So this is alpha over 1 minus alpha minus the limit as n goes to infinity. This is 1 over 1 minus alpha. I could factor that out if I want. Alpha to the n plus 1. So I have to look at this. What is this limit? So this limit exists if and only if alpha to the n plus 1 goes to 0 as n goes to infinity, which only happens when alpha in absolute value is less than 1. So now we have the correct statement of the series in geometric, on the theorem about geometric series. If alpha is a number less than 1, then summation alpha to the n goes from 1 to infinity, converges And the limit is alpha over 1 minus alpha. And if the absolute value of alpha is greater than or equal to 1, then this infinite series, the geometric series, diverges. So this is something that anyone taking a 300 level math class absolutely positively has to know, especially if you're going to be teaching math in the high school, for example. So this is the theorem about geometric progressions. And again, this is used a lot in the end of Math 176, Calc 2. And if you take more advanced math classes, this very, very often comes up. Now, in the 18th century, this was the time when Newton invented calculus, though he didn't tell anyone for 50 years. And simultaneously and independently, a German mathematician, Leibniz, discovered the same thing, the same kind of, well, basically independently discovered calculus, if you like. And when he was very young and beginning to study mathematics, as is described in the text, his teacher asked Leibniz to try to figure out whether another infinite series converged or diverged. So for this, you have to know something about not geometric series, but geometric numbers. So the geometric numbers that everyone knows are the squares. 1, 4, 9, 16, and so forth. And one reason they're called geometric numbers is because each square, well, there's 1. If you have the number 4, it's just the number of points in this little square. Right? This is 1, this is 4. For 9, you can draw a square with 3 of length, well, 3 dots on each side. That's 9. 16, that's 16, right? So these are all somehow built up from squares, and 25 and so forth, right? These are the square numbers. But there are also numbers that are called triangular numbers, and they're numbers that come from triangles. Of course, that's a simple triangle. There's just 1 dot there. So here's a triangle. There are 3 dots. The next triangle, you might have 3 dots in the base, and every time you go up, you have 1 fewer dot. If you count up the number of dots, so this is 3, which is 1 plus 2. Here I have 1 plus 2 plus 3. I have 6 dots. That's the third triangular number. If I take 1, 2, 3, 4, you have 10 dots, which is 1 plus 2 plus 3 plus 4. What's going to be the next triangular number? You'll have triangle with 5 dots on each side. There it is. And each time you get the previous number by adding 1 more row, which with 1 more dot. So here, 1, 2, 3, 4, 5. That's 15. You would expect the next triangular number to have an additional 6 dots. So 15 plus 6 is going to be 21. And again, if you sort of start building your triangle, 1, 2, 3, 4, 5, 6, you have 21 dots. So this defines the triangular numbers. So the nth triangular number is the number of dots in these bigger and bigger triangles. It's just the sum of the first n integers. Which you might know is also n times n plus 1 over 2. Right? So you might want to check that this is correct, that the sum of the first n integers is n times n plus 1 over 2. And the Leibniz problem, the problem that was given to Leibniz was compute, if it exists, the sum of the reciprocals of the triangular numbers. That is, the first number is 1, 1 over 1 is 1. The next number is 3, so it's 1 plus a third. This next number is 6, so that's 1 over a 6. The next number is 10, so it's 1 over 10, 1 over 15, 1 over 21, and so forth, right? So here we have this infinite series, which is the sum of the reciprocals of the triangular numbers. And what is it equal to? Yeah.
2?
Question?
No. Is it equal to 2?
Well, why did you say that?
Well, because we started with 1, and from there on it keeps increasing. The partial sums keeps increasing. We have 1/3, 1/6, but as it increases, the turns that the next term that keeps adding on is decreasing, but it never goes to negative. So I'm thinking maybe we go to 2.
Well, I mean, it certainly can't become negative because you're only adding positive things. But if you took the series, the harmonic series, 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, by your reasoning, would you say that also goes to 2?
Yes. Yeah.
Okay. So the great theorem in this chapter, which I'll prove in a few minutes, is this series diverges. This goes to infinity. Right? This series converges to 2. So you were right about that. But since the same reasoning was applied here and here, and you got the same answer, let's just say you were a lucky guess. It was a lucky guess. But if you did that on the exam, you would get full credit because you got the right answer.
I guess.
Right? So, it's like, if you solve the problem, you get the credit. So, and no one cares how you solve the problem if you get the right answer. So even though these series look similar, the terms are going to 0, but in this case, the series diverges. In this case, the series converges. And in the text, this is on pages 186 and 187. It draws pictures of at least these first 4 triangles. But how does one prove this? Or how did Leibniz prove this? That's really the question we have to answer. So Leibniz's proof. So we have S is 1 plus a third plus a sixth. So I'm just going to do it in the sloppy way that people, I mean, in retrospect, we consider this pretty sloppy because it doesn't satisfy modern standards of rigor, but you still got the right answer. So the first thing Leibniz did, for whatever reason, is divide by 2. So instead of looking at s, he looks at a half s, which is a half plus a sixth plus a 12th plus 1/20th plus 1/30 plus 1/42 and so forth. You're just dividing by 2, which means you divide every number by 2. But then he makes the following observation. A half is 1 minus a half. And the sixth is a half minus a third. And a 12th is a third minus a fourth. And a 20th is a fourth minus a fifth. And 1/30 is a fifth minus a sixth. And 1/42 is a sixth minus a seventh. And this pattern continues. But now when you look at this, you see you have minus a half plus a half, they cancel. Minus a third plus a third, they cancel. Minus a fourth plus a fourth, they cancel. Minus a fifth plus a fifth, they cancel. Minus a sixth plus a sixth. Everything cancels, and you're left with just 1. So a half s equals 1. So just as you predicted correctly, if a half s is 1, s is 2. Right? So yeah. And this was Leibniz's proof. You can modify this a little bit the way I did a few minutes ago with the geometric series and get essentially the same proof, which is completely rigorous by current standards. But this is already pretty good. So S is equal to 2. Right? This is Leibniz's theorem. Now, the open problem, apparently, in the 17th century was, does the harmonic series converge? So that's the series 1 plus a half plus a third. So now you're taking the reciprocals of all of the integers. Does that series converge or diverge? And the following was the argument that one of the Bernoulli brothers made to solve this problem. This goes back to the 17th century, 1689, Bernoulli. And the way he solved the problem was kind of miraculous. And it goes as follows. So let's just forget the 1 for the moment. Adding 1, if the series converges, you add 1, you get the sum is just 1 bigger. I'm just going to look at the series starting with a half. So suppose we let A be the series a half plus a third plus a fourth plus a fifth plus a sixth and so on. It's the sum of the reciprocals of all the integers. And I'm just going, so here the fractions are in lowest terms. I'm just going to write each fraction such that when you look at the numerators, the sequence of numerators of the new fractions, instead of being 1, 1, 1, are 1, 2, 3, 4, 5, and so forth. So I have a half If I want to write a third as a fraction with the numerator 2, then the denominator has to be 6, right? Because 2 over 6 is a third. If I want to write a fourth as a fraction with the numerator 3, then 1/4 is 3 over 12. 1/5 is 4 over 20. 1/6 is 5 over 30, and so forth. Okay? So that's what this series looks like. Now, that's A. Sorry. That's, well, actually, if you want to look at the extract from Bernoulli's book written in 1713, this is A. This is the same thing, but they call this B. So A is this series, B is exactly the same series, but now you write each fraction not in lowest terms, but so the sequence of fractions have numerators going 1, 2, 3, 4, 5, and so forth. Okay. Now, if you remember the series of triangular numbers, let's call that C. The triangular numbers were let's see. Let me do this slightly differently. Remember we have the triangular numbers. And the sum of the, so 1, 3, 6, 10, 15, 21, and so forth. And the sum of the reciprocals, 1 plus a third plus a sixth plus a tenth plus 1 over 15 plus 1 over 20 and so forth, was equal to 2. So if I drop the 1, or I subtract 1 from both sides, I get, no, that's okay. Let me just leave it like that. Divide by 2. So 1/2, 1/3 divided by 2 is a sixth. 1/6 divided by 2 is a 12th. 1/10 divided by 2 is 1/20th. 1 over 30 and so forth equals 2 divided by 2, which is 1. So from Leibniz's theorem about the sum of the reciprocals of the triangular numbers, we get this series, which I'll call C, which is 1/2 plus a sixth plus a 12th plus 1 over 20 plus 1 over 30 and so forth equals 1. Suppose I subtract 1/2 from both sides of this equation. So if I subtract 1/2, this term is gone. I get 1/6, 1/12, 1/20th, 1 over 30, and so forth, is 1 minus 1/2. So I'm subtracting the 1/2 equals 1/2. And now let me subtract a sixth from both sides of this equation. I get E equals 1/12 plus 1 over 20 plus 1 over 30 and so forth is 1/2 minus a sixth, which is a third. And then I subtract a 12th from this. And all of this is done if my writing is bad, as it always is. Just this is all on page 197. Subtract a 12th. I get 1 over 20 plus 1 over 30 and so forth is a third minus a 12th, which is 4/12 minus 1/12 is 3/12. It's a fourth. And if I subtract 1/20 from both sides, I get a fourth minus a 20th, which is a fifth, and so on. And now, so I do this infinitely often, and add these equations. I get a half. I have a 6 plus a sixth, which is a third, a 12th plus a 12th plus a 12th. That's 3/12. That's 1/4. I have 4/20, which is a fifth. I have 5/30, which is a sixth, and so forth. I get that. And on the right-hand side, I get 1 plus a half plus a third plus a fourth plus a fifth, and so forth. And this is equal to this. So if A, what was A? A is the harmonic series without the 1. This is A. So this says that A is equal to 1 plus A. Right? Well, no number is equal to 1 plus itself, except maybe infinity. So A is infinite, and the harmonic series diverges. So this is the great theorem in chapter 8. It's Bernoulli's proof of the divergence of the harmonic series. Right? Now, in Math 176, this is proven, but by a different method. But this is Bernoulli's proof. And people used to say that Bernoulli was the first person to prove the divergence of the harmonic series. Right? But it's kind of like, if a tree falls in a forest, doesn't make us, and no one is around, doesn't make a sound. Right? So it's not like today when everything is on the internet, and whenever anyone proves a theorem and publishes it somewhere, it's accessible. So it turns out, even though no one in France or Germany or Switzerland at the time knew how to prove the divergence of the harmonic series, in fact, it had been proved previously. And not only proved previously, but proved previously and in different ways by different people. So before Bernoulli, an Italian mathematician named Mengoli also proved the harmonic series diverges. And he did it by using the following inequality. Inequality is if A is bigger than 1, then 1 over A minus 1 plus 1 over A plus 1 over A plus 1 is bigger than 3 over A. Let's see. How do we prove this? So this is the same as saying, because I have a 1 over a here and 3 over a here, it's enough to show that 1 over a minus 1 plus 1 over a plus 1 is bigger than 2 over a. So this is, let's put this over a common denominator. 1 over a minus 1 plus 1 over a plus 1 is a plus 1 over a minus 1, a plus 1, plus a minus 1 over a minus 1, a plus 1, right? Here I just multiplied numerator and denominator by a plus 1. Here I multiplied numerator and denominator by a minus 1. So this is a plus 1 over a squared minus 1, a minus 1 over a squared minus 1. When I add, I get 2a over a squared minus 1. And let's see, this is, I want to show this is greater than 2a. So this is greater than 2a if and only if, when I cross multiply, 2a squared is bigger than 2 times a squared minus 1. Divide by 2, a squared bigger than a squared minus 1, or 1 is bigger than 0. So this is true. So we're done. So I just proved this inequality. For example, if I take a equal 4, this says a third plus a fourth plus a fifth is bigger than 3 over 4. Let's see, is that right? I don't know. If I put this over a common denominator of 60, this is 20 plus 15 plus 12, which is 47 over 60. And 3 over 4 is 45 over 60. This is bigger than 45 over 60. So this is just an instance of this inequality. Right? So I have this inequality. Let me write it down again. For all a bigger than 1, 1 over a minus 1 plus 1 over a plus 1 over a plus 1 is bigger than 3 over a. So in 1647, Mengele used this to prove the divergence of the harmonic series. So suppose we let h, for harmonic, be the sum be the harmonic series. So I can think of this as 1 plus a half plus a third plus a fourth. See, this says if you take the reciprocals of 3 consecutive integers, that's bigger than 3 times the reciprocal of the middle integers. So if I have a half plus a third plus a fourth, this is bigger than 1 over 3 times a third. Then I have the 3 numbers with denominators 5, 6, and 7. This is bigger than 3 times a sixth. And then I have an eighth, a ninth, and a tenth. That's bigger than 3 times a ninth. And if I take the next terms, 1 over 11, 1 over 12, 1 over 13, this will be bigger than 3 times a 12th, and so forth. This is 1 plus 3 over 3 is 1, 3 over 6 is 2, 3 over 9 is 3, or third, 3 over 12 is a fourth. So I get h is bigger than 1 plus, but then what I have is 1 plus a half plus a third. That's 1 plus h. So this says h is bigger than 1 plus h. Well, I could stop right there. That just says that's ridiculous because 0 is not bigger than 1. Or what Mengoli did was saying this is bigger than 1 plus h, which is 2 plus h, which is bigger than 2 plus 1 plus h, which is 3 plus h, and so forth. And ridiculous, impossible. So therefore, h does not exist. There's no h that is the harmonic series must diverge. So we actually have now 3 different results about infinite series. So we have the geometric series. One plus alpha squared plus alpha cubed, so on forever, which equals 1 over 1 minus alpha if the absolute value of f is less than 1 and it diverges, the absolute value of alpha is greater than or equal to 1. We have the triangular numbers, the reciprocals of them. 1 plus a third plus a sixth plus a 10th plus a 15th and so forth. And this converges to 2. Right? This was Leibniz's theorem. We have the harmonic series. One plus a half plus a third plus a fourth and so forth. This series diverges. That was Bernoulli's result. What about other series? Well, what about if instead of taking the reciprocals of the triangular numbers, you take the squares? That is the sum of the reciprocals of the squares. The squares 1, 4, 9, 16, 25, and so forth. So what about 1 plus a fourth plus a ninth plus a 16th plus a 25th? What is the next square? 36. 1 over 36, 1 over 49, and so forth. Does this series converge or diverge? If it converges, what is the sum of the series? Now, this was also for a long time an open problem. And Bernoulli proved, let's see, in sigma notation, how will we write this series? This is summation. K goes from 1 to infinity, 1 over k squared. Right? That's this infinite series. Summation 1 over k squared. K goes from 1 to infinity. Bernoulli proved this series converges, but could not find the limit. So this is interesting because you would think if you can prove the convergence at the same time, you would know what it what the terms add up to. But that Bernoulli couldn't do. So this is interesting. So he could prove the convergence without being able to figure out what was the limit. And he did this by what today is called a comparison theorem. So the comparison theorem would say something. Suppose we have two sequences, summation a sub k, k goes from 1 to infinity, and summation b sub k, k goes from 1 to infinity. And suppose these terms are non-negative, and ak is always less than or equal to bk. So one part of the comparison theorem says if summation bk converges, then summation ak converges. And the idea behind the proof is, if you look at the partial sums of the series of a's, ak, k goes from 1 up to n, since each ak is less than each bk, this will be less than summation bk, k goes from 1 up to n. Call that S sub n prime, say. And if this series converges, these numbers are getting bigger and bigger and bigger, but they'll be less than some number s, less than infinity. Which means if you look at the partial sums of the A series, they're going to get bigger and bigger, but they're going to be bounded above, which means they have to reach some kind of limit. But this is the comparison test, or one part of the comparison test, which is also part of the Math 176 curriculum. And back in the beginning of the 18th century, end of the 17th century, this is in effect what Bernoulli used to prove the sum of the reciprocals of the squares converges. So Bernoulli observed the following identity. For any k positive integer, 1 over k squared is less than 1 over k times k plus 1 over 2. Let's see. Proof. Let's see. If we cross multiply, that's the same as saying, so if this fraction is less than this fraction, this denominator has to be bigger than this. So k plus 1 over 2 is less than k squared. And if you cancel the k's, that says k plus 1 over 2 is less than k, which means k plus 1 is less than 2k, which is true whenever, subtract k, k is bigger than 1. So these are equal when k equals 1, but for k greater than or equal to 2, this fraction is strictly smaller than this fraction. And here is the important point. This number is a square. And this number, this is the triangular number. 1 plus 2 plus 3 up to k is k plus 1 over 2. So if I take 1 plus a fourth plus a ninth plus a 16th plus 1 over 25 and so forth, the sum of the squares, this is bigger than 0. These are all positive numbers. This is less than 1 plus, let's see, when k is 2, a third. When k is 3, a sixth. When k is 4, a tenth. So each term in the series 1 over k squared is this series converges. This series, this is summation, k goes from 1 to infinity, 1 over k, k plus 1 over 2. This is summation 1 over k squared. K goes from 1 to infinity. And this is equal to 2. So this series converges to something less than 2. So this is Bernoulli's proof that the sum of the reciprocals of the squares converges. And the open problem was, what does it converge to? Right. So now we're moving into the 18th century. And so the unsolved problem, or let me just put it this way, it's not unsolved now. The problem unsolved by Bernoulli was to compute exactly the sum of the reciprocals of the squares. And this is what we discuss in the next chapter. The next chapter, chapter 9, is called The Extraordinary Sums. Extraordinary sums of Leonhard, E-U-L-E-R, and this is pronounced Euler. So Euler, in 1734, proved the following great theorem. And this is truly a miraculous theorem. And I don't know of any easy proof of this theorem. So there's going to be more work involved in this chapter than there had been in any of the previous chapters, I think, which is summation 1 over k squared. K goes from 1 to infinity. He computed exactly what it's equal to. And why it's equal to what it's equal to is a little bit mysterious, because there's nothing geometrical in any obvious way about this, certainly not connected to circles, for example. But it turns out the sum of this series is pi squared over 6. Right? So this result earns a lot of stars. Right? Right? See, pi squared over pi is 3.14. Pi squared is about 10. So this is about 10 over, about 5/3, something of that sort. Has to be less than 2, because we know it's less than the sum of the reciprocals of the triangular numbers. This is definitely less than 2 and certainly bigger than 3/2, bigger than 5/4. But it's exactly equal to pi squared over 6. And that is what we're going to talk about in the next chapter. It's going to depend on some things that you should have seen in Math 176 when you're studying Taylor series. So, for example, this is a Taylor series. And it'd be good if you have your calculus book just to go back and review this. Sine x is a very transcendental, complicated function. But algebraically, this is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So this is an infinite series, but if you truncate it at any point, you get a polynomial approximation to the sine. the sides alternate, plus, minus, and the powers of x are consecutive odd powers of x divided by the power of the factorial. So x to the minus x to the 7 over 7 factorial. The next odd number is 9, and after minus comes plus. So this will be x to the 9 over 9 factorial minus x to the 11 over 11 factorial plus x to the 13 over 13 factorial and so forth. And if you stop this at any point and just look at the polynomial, that's a good approximation to sine of x. And the more terms you get, of course, the better the approximation. You would just take the first two terms, for example, you would say sine x is approximately x minus x cubed over 6. So on. So this is what I'm going to be talking about on Wednesday. And my plan is before the next exam to cover chapters 9 and 10. So the second midterm exam, which is 2 weeks from Wednesday, which is, I guess, the 17th of April, will cover chapters 6 through 10. So there's a lot of material there to study. Right? Any questions about this? There's a lot, we're covering a lot of material in this course. That's part of the course. But it's very, very beautiful, very valuable, and not just historically significant, but still a major part of modern mathematics. So everything we learn today is really good to know. If you have questions, I have Zoom sessions this week, today, tomorrow, Thursday at 7 o'clock. And if you have questions but can't make any of those regularly scheduled sessions, just send me an email and we can work out a time. All right. Anything before we quit for the morning? Okay. All right. Be well, all. See you Wednesday morning.
All right. Have a good day, Professor.
Thank you. You too.